Alright guys, today we're going to be looking at our energy unit and reviewing the different energy calculations and things that we've covered over the past month and a half or so. Hopefully it'll be a good refresher after all of this time off. Let's go ahead and jump into it. So first of all, we want to talk about what essential skills we're going to be talking about in this video, and we're going to be looking at 4 major skills that we want to cover. First is going to be being able to identify the types of energy present in a system. Number 2, be able to describe energy transfers and transformations within a system. Number 3, apply basic energy formulas to calculate kinetic, elastic, and gravitational potential energies. And then number 4 is going to be using the conservation of energy to do some calculations for objects within a closed system. So let's start by looking at essential skill number 1, be able to identify the types of energy present in a system. In order to identify the different types of energy present in the system, we first have to understand what energy actually is. And energy is the ability to do work. For our purposes, energy is effectively the ability to put an object into motion. It doesn't always have to be related to motion. It can also be things like heat or chemical energy. But for our purposes, since we're only really looking at 3 major types throughout this unit, we're going to focus on the ability to put objects into motion. And energy takes different forms, as I was just saying. Some of those forms include things like thermal energy, which is like heat, chemical energy, which is the energy that's actually stored in bonds between different atoms. It's the type of energy that's in your body that lets you do different things. That's why you have to eat food, stuff like that. Electrical energy, this one's pretty obvious. Things like the electricity that runs your computer, your house, whatever, your phones, etc., etc., which is actually developed from other kinds of energies. There's also light energy, which is separate from either of those, but effectively very similar to both heat and electrical. The 3 that we actually care about, though, are gravitational potential energy, which is energy due to position, specifically usually height. There's kinetic energy, which is the energy due to motion, and there is elastic potential energy, which is the energy due to the compression or stretching of an object. The majority of energy on Earth can actually be traced all the way back to the sun. There's some energy that started as geothermal energy within the planet, but for the most part, most of the energy we get in our daily lives actually comes from the sun. And it does that by constantly moving and changing throughout the world. So it usually comes into the planet in the form of light or heat. Heat can be absorbed directly by a lot of different things. Energy, most commonly, or at least most useful to us, is going to be absorbed by plants, where it can be converted into chemical energy. We can consume that chemical energy. We can use that chemical energy to move ourselves, to move other things, etc., etc. And because of this complex nature of energy and its ability to cycle through the environment and things like that, we need to make sure we can actually narrow down and focus on a small point. And that becomes very difficult if we try to look at all the energy physically possible within a system. If we're looking at the chemical energy behind a person that's riding on a skateboard and the heat energy that's being formed as they breathe and things like that, it's too much stuff for us to consider all at once. So in physical science and physics in general, we like to consider what are called closed systems. And in a closed system, we try to limit our considerations to only the objects that actually matter to us. So in this case, we have a skateboarder riding on a ramp, and the objects that really matter to us here are just the skateboarder and the ramp itself. Really, like, you can see some mountains in the background, the sun is probably somewhere, there's probably some wind going on, and we could think about, like, the skateboarder's clothes and, whether he bends his knees or bends his arms or whatever else, and maybe some of those things will have a little bit of an effect, but they effectively don't matter. We call them negligible forces most of the time in physics. We don't need to worry about those. So we can really treat the skateboarder and the skateboard itself all as one object, and then we have the ramp. So we'd just be looking at those 2 different things within this closed system. Now, once we've established a closed system, we can start looking for different types of energy. And the 3 main types of energy that we've focused on are gravitational potential energy, kinetic energy, and elastic potential energy. An object will have gravitational potential energy if it has the potential to fall. So generally speaking, if you see a height in a problem, you're going to be getting a gravitational potential energy. Kinetic energy is the energy of motion. So in order for an object to have a kinetic energy, it has to have a mass and it has to be moving. If you're given a velocity, you're almost certainly going to have a kinetic energy. Lastly, we look at elastic potential energy. An object will have elastic potential energy if there is a spring or if an object is compressed or stretched. Generally, what you're going to see is a spring constant, and we'll talk about that in a little bit, but hopefully you guys remember spring constant is denoted by the letter K, and spring constants are just the stretchiness of an object. So now that we've identified or talked about the different types of energy that we're actually going to be using, we can look at some practice identifying energy examples. So in each of the following examples, you're going to decide which of the three energy types you would see in that example. We are going to be looking at these pretty quickly, so it might be worth it to pause the video and actually get a chance to practice on your own, but hopefully this shouldn't be too difficult just yet. So the first one we're going to look at is a speeding car. So the types of energy in a speeding car. I'll give you a couple seconds to consider that. And of course, a speeding car, because it's going to have a speed, a velocity, we know that it's going to have kinetic energy. It could potentially have potential energy, but we don't know enough about it right now to say whether or not it does. It also will have chemical, but again, that's not one of the three main energy types that we're looking at here. A ball being held in the air. Once again, I'll give you a minute to think about it for yourself. And of course, the ball being held in the air is going to be gravitational potential energy. There's probably something holding it that has other types of energy in it, but we don't really care about that. We're just looking at the ball itself. And of course, since it is being held in the air, it is not on the ground, it has the ability to fall, so it is going to have gravitational potential energy. Next example, a slingshot being pulled back and ready to be fired. And of course, a slingshot is going to be an object being stretched. It will have some kind of spring constant attached to it. We don't really need that to know that it's going to be elastic potential energy that we have in this system. There's probably gravitational potential energy because it's being held up by somebody, presumably, but again, not really what we're talking about right here. We're mostly looking for the elastic. Now, this last example is actually going to have multiple types, and we've actually got a picture going with it, so it'll be a little bit easier for you to identify. But we're looking at a skateboard that is halfway down a ramp. So assuming that he started at the top and has been rolling down, wherein he is at this position right here that we can see on the screen right there. At that position, what kinds of energy is the skateboarder going to have? Just a second. And of course, we know that since this skateboarder still has the potential to fall lower, he still has gravitational potential, and because he is in motion already, we know that he has kinetic. Also, if you looked closely at that picture, you would see that it's actually telling you the answer, but that is okay. So next up, now that we've practiced identifying the types of energy present in a system, we're going to look at describing energy transfers and transformations within a system. In order to do that, we first need to define the terms transfers and transformation. Now, transfers and transformation come from the law of conservation of energy, and the law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred or transformed. What that actually means is that energy is transferred when it moves from one object to another. So a baseball bat to a baseball, something like in a car crash, whatever the car crashes into, transfers energy from the car to the object that it hits, things like that. Transformation is when it actually changes from one form of energy to another. So if you have gravitational potential energy to kinetic energy as a ball begins to fall or as our skateboarder begins to go down the ramp, as the skateboarder gets turned back up the ramp, you'll see thermal energy forming as a result of the kinetic energy and the friction between the ground. Again, we're not really going to look at that, but that is another type of transformation. There's also gravitational potential energy to, say, elastic potential energy in the case of the bungee jumper that we were looking at before. One last thing to keep in mind is that transfers and transformations can happen at the same time. This can be a little bit confusing, but just keep in mind that if energy is ever moving from one object to another, it will always be a transfer, and whenever energy changes from one form to another, you know there's going to be a transformation. So let's do a little bit of practice with this. What kind of transfers and transformation would you expect to see in the following examples? So we're going to look at that skateboarder again. I'm going to give you guys just a minute to talk or think about this on your own before I talk about it. Okay, so what we're going to see here is up at the top, the skateboard is going to have a lot of gravitational potential energy. As he drops in, he's going to have that energy transforming into kinetic energy as he reaches the bottom, and then it will transform back as he goes back up the other side. And assuming there is friction on this, you're also going to have a transformation of kinetic energy into thermal energy as he starts to slide across that ramp and turn sharply. And that is also going to be not just a transformation from kinetic to thermal, but also a transfer from the skateboard to the ramp. Let's move on to the next example. This is a person jumping off of a platform of some kind and bungee jumping. So at position 2, that is when the cord is just starting to stretch. At position 3, that's when that cord is stretched out to its maximum. But looking at the entirety of the jump, what kind of transfers and transformations would you expect to see there? So at position 1, we see that this person is going to have exclusively gravitational potential energy as they're not moving and there is no elastic energy being or forming just yet. As they jump, that gravitational potential energy is going to transform into kinetic energy until they hit position 2, where you're actually going to start having elastic potential energy coming into the equation as that bungee cord begins to get stretched. So that will be a transfer of kinetic and or gravitational potential energy into from the person's gravitational or kinetic energy into the elastic energy of the bungee cord. So the transfer is happening from the person to the cord, and the transformation is happening from kinetic / gravitational potential into elastic. At the bottom, they no longer have any velocity, so their kinetic energy has all been transformed into elastic potential and transferred to the bungee cord. And then, of course, as he's going to shoot back up, that elastic potential energy is going to be transformed and transferred back into kinetic energy in the person. So now that we've looked at transfers and transformations, we'll go ahead and move on to applying some basic energy formulas to calculate kinetic, elastic, and gravitational potential. And of course, first we're going to actually review these formulas. So starting with gravitational potential energy, it's good to keep in mind that when we're calculating energy amounts in general of any kind, the resulting energy is always going to be measured in joules, which is denoted with a capital J. So for gravitational potential energy, our energy formula is GPE equals mgh, and when we get to some practice, we'll be using this formula a few times, where m represents the mass measured in kilograms, which is denoted as lowercase kg. G represents the acceleration due to gravity, so you can think of it just as gravity, and it's 9.8 meters per second squared on Earth. If we did calculations for some reason about something on the moon, that G value might change, but in general, assuming that we're doing any normal problem, you can always use 9.8 to represent G. And then H represents the height measured in meters. So looking at an example problem, which I will give you a minute to do on your own, an object with a mass of 2 kilograms is suspended 10 meters in the air. How much gravitational potential energy does it have? And that same problem is written right here. I'm going to go ahead and give you guys a little bit of time, pause the video, and we're going to work through it together. Okay, so working this problem out, first we want to start off with our formula. And since this is gravitational potential energy, we just covered that GPE equals mgh. In this case, we know that our mass is 2 kilograms. Gravity is, of course, going to be 9.8. This equals mass. And our h, we know, equals 10 meters. So all we have to do is do 2 kilograms times 9.8 meters per second squared times 10 meters. And that will give us a total of, when we plug that into a calculator, 196. And since it's energy, and we just said energy is always measured in joules, this is our final answer. Oops, sorry for kind of screwing that up here. Let me put it in bigger font. This new pen is a little bit difficult for me to use. I haven't had a lot of practice with it, but 196 joules. All right. Moving on to kinetic energy, the formula for kinetic energy is Ke equals 1/2 mv squared, where m is again the mass measured in kilograms, and v is the velocity, which is measured in meters per second. So velocity, of course, is just a speed with a direction. If you'll notice that unlike the gravitational potential energy formula, which is mgh, our formula for kinetic energy has an exponent, that v squared. This actually means there's a quadratic relationship between velocity and kinetic energy. And so if you remember, in a quadratic relationship, when x doubles, y quadruples. So in this case, when velocity doubles, our kinetic energy will actually quadruple. For this example problem, we have an object of mass, or with a mass of 10 kilograms traveling at 5 meters per second. How much kinetic energy does it have? So I'll give you guys just a second to work on that on your own. You should probably pause the video, take a shot at it, and then I will go over it really quick as well. And these should all be review. Hopefully you guys remember this stuff from when we were doing it in class. But just in case, it has been a long break, so we'll go ahead and go over it anyway. Okay, so to solve this problem, we get to start with our formula. Ke equals 1/2 mv squared. And in this case, our m equals 10, our v equals 5. So I guess I can put the units here, kg and meters per second. So in this case, we've got 1/2 times 10 kg times our velocity, which is 5 meters per second squared. And of course, this is going to equal 25. That 5 squared. This 1/2 times 10 is going to equal 5. So we get 5 times 1, or 5 times 25. You can also just plug this into a calculator, and we will get 125 joules. So that is how we solve the kinetic energy problem. And the last one we're going to look at is elastic potential energy. The formula for elastic potential energy, hopefully you remember this one as well, it is EPE equals 1/2 kd squared, where k is the spring constant, which is the stretchiness of an object, measured in newtons per meter, and d is the distance stretched measured in meters. Now, d can occasionally be replaced with an x. I think advanced physics classes tend to use x, but we were using d a bunch. Either one works just fine. Just remember that that is the distance that the object has actually been stretched. So generally speaking, this will be like if a spring is stretched or compressed, that d is the distance that it actually was from its neutral point. Like kinetic energy, this formula also has an exponent, which means there's also a quadratic relationship. In this case, it is between the distance stretched and the elastic potential energy. So for the example problem for this one, we have a spring with a spring constant of 1200 newtons per meter, stretched 0.2 meters. So how much elastic potential energy does that have? Once again, take a minute, try this on your own. Go over it in just a second. All right, starting as always with our formula, we've got EPE equals 1/2 kd squared. And in this case, we've got a k of 1200 newtons per meter. Sorry, that got a little rough. And our d equals 0.2 meters. That is an m. 10 trouble. So here, all we got to do, 1/2 times 1200 times 0.2 squared. And that, when we plug that into a calculator, is going to give us 24 joules. And that is how we solve that. So lastly, we want to use the conservation of energy to do some calculations for objects within a closed system. So that's our essential skill number 4 here. And to do this, we're going to need to use that law of conservation of energy. So I'm going to restate it here. The law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred or transformed. For us, in this case, that means that whenever we're working with a closed system, the total energy in that system must remain the same. And assuming that we can calculate the energy at one point in the system, we should be able to calculate the energy at other points as well. So we did this a bit with the bungee jumper examples in class, but we're going to go ahead and try a couple little practice ones in just a second. First, it might actually be helpful to look at the entire total energy formula. So right here in this section here, we've got the total energy formula written out entirely. So you'll notice that this is just gravitational potential energy plus kinetic energy plus elastic potential energy right here. And then down here, we've got that same thing, but we actually wrote out, we wrote out the formulas for them. So mgh plus 1/2 mv squared plus 1/2 kd squared. And of course, that gives us our total energy. We can then use that to solve problems later. So we're going to look at an example of our skateboarder in order to practice these calculations. So right here, I added some numbers to the image, so we've got some numbers we can use for the calculation. So the first thing we're going to try to look at is the skateboarder's total energy at this position right here, and we're going to call this position 1. Right? Now, he is falling down the ramp and he has a speed, so we know that he has a kinetic energy. And we know that since he's still not on the ground, he has a gravitational potential energy. For Ke, we know that that is 1/2 mv squared. For gravitational potential, we know that's mgh. And in this case, we have 1/2 times our mass, which is 3 kilograms, times our velocity squared, 1.5 squared. And that is going to give us 3.375 joules. Our gravitational energy, we've got m, which is 3, times 9.8, times our height, which is 5, equals 147 joules. So in this case, we've got a much bigger gravitational potential energy than we have a kinetic. And then once we add these up, we get 150.375, or about 150 joules. So that is the total energy at position 1. Now, you'll notice that we didn't bother with elastic potential energy here. That's because there's no spring anywhere. We don't actually need to use that formula to solve this problem. But we're going to go ahead and take a look at a couple more. So this next one, now we're going to try to see if we can calculate his fastest possible velocity. And we're going to assume that this is frictionless, so don't worry about thermal energy or anything like that. So what we're going to be trying to do is calculate the velocity of this skateboarder at position 2. And that might look difficult for us, but if we remember, our total energy equals our gravitational potential energy plus kinetic energy plus our elastic potential energy. Now, we actually know total energy from the last problem. Since our energy is conserved within this closed system, and we already calculated that he has 150 joules of energy, and yes, that is rounded, but that's okay, it's going to make our calculations easier. We know that 150 joules equals GPE plus KE plus EPE. Now at this point, at point 2 over here, we actually have a height of 0, and there's still no spring, so this is going to be 0, and this is going to be 0, leaving us with just 150 joules equals our kinetic energy. Since we know that the formula for kinetic energy is 1/2 mv squared, we can say that 150 equals 1/2 mv squared. And since the mass presumably is the same, I'm assuming that this skateboarder didn't lose any weight on his way down the ramp. We know that 150 equals 1/2 times 3 times v squared. Now in order to solve this, we'd multiply each side by 2 and divide by 3. So that's going to give us 100 equals v squared, which gives us, if we take the square root of both sides, that will give us a v equals 10 meters per second. So there you go. Using our total energy and that conservation of energy rule, we were able to calculate our energy at this bottom point to be the same as at our first point, and that gives us a velocity of 10 meters per second. We're going to try one more. I'd like you guys to try to take a chance at this one on your own, so go ahead and pause the video, see if you can do this, but we're going to try to calculate the skateboarder's maximum possible height at point 3. Now remember, at this point, when he hits this top area, his velocity is going to be 0. There's still no spring, so hopefully that will give you enough of a hint. But go ahead, pause the video, take your best shot at this, and then we'll go over it together. So to work this problem, we know we're going to have gravitational potential energy as the only form of energy that we have, since we have this V of 0 and we have no spring. So GPE equals 150. We know that that's the same as before. And in this case, that means that 150 equals M times G times H. Now, 150 equals, we have a mass of 3. We know that G is 9.8. So we just need an H. And once we divide both sides by 3 times 9.8, these will cancel. Divide by 3, 9.8. We're going to be left with an H of 5.1 meters. And you'll notice that actually means that where we started looking at it, he was pretty much at his maximum height. But that is okay. So we were able to calculate the height based on just knowing the total energy, using that conservation of energy formula and solving for height. Now, hopefully you guys recognize this example. This little chart right here is our bungee jumper. We used this a few times, and hopefully you also remember these. We're not going to go over those in this video. We might do another one reviewing them later, but remember these are just transfers of energy. So this red represents gravitational, the green represents kinetic, and the blue represents elastic potential. And then our total energies, you'll notice, are the same in every single situation. So what we are going to look at for our practice is at position 1, we've got this jumper right here. He has a mass of 5 kilograms. There's a height of 10 meters. And at the end, we've got a height of 1 meter. And our job is to calculate the elastic potential energy in the bungee cord at position 4, right here. So go ahead, pause the video, see if you can do that on your own, and then I will go over it with you as well. Okay, so this one's a little bit more complicated. We have to start out by calculating the energy at position 1 first, so that we have our total energy. So at position 1, all of our energy is gravitational potential. He's not moving. We don't have a spring that's starting to stretch just yet. So we have GPE, and that is equal to mgh. In this case, that is equal to 5 times 9.8 times 10. And that's going to give us a total of 490 joules of energy. So 490 joules of energy at, joules at position 1. Now that we know that, we know the total energy of our system is equal to 490. So at position 2, we can calculate the GPE, which will still equal mgh, still 5 times 9.8, this time times 1, because our height is only 1 down here. This is going to give us 49 joules of energy. Now, at this position right here, we've got a stretched out bungee cord. This should be completely stretched out, but that's okay, it's close enough. He is actually no longer moving at this point because he's reached the very bottom of his jump. He's about to spring back up, which means that we don't have any kinetic energy to worry about here. You can see here there's no green. That's because there's no kinetic energy at this point. So all the rest of the energy in our system is going to be elastic. Now, our elastic energy, of course, is equal to 1/2 kd squared, but it's also equal to, in this case, our total energy minus our gravitational potential. And that's because if we solve that other formula for elastic potential energy, we just get that as total energy minus gravitational minus kinetic. We don't have any kinetic, so it's just total energy minus gravitational. So we know that all the energy left in our system, which is 490 is the total, is going to be elastic potential. So all we have to actually do here is 490 joules minus 49 joules, which is going to give us a total of 441 joules. And that is our total elastic potential energy here. There's going to be more practice on problems like this in some of the other videos. There'll be essential skills practice videos. There'll be some basic ones and then more like this where you have to calculate specific values based on the conservation of energy in different positions that you're given. But for now, let's go ahead and look at this right here. So to review, I'm going to go ahead and go over these things really quick one last time. Hopefully this whole thing was a review, so hopefully this wasn't too much. I know it's a lot of information to go over, but I think you guys can handle it. Energy is the ability to work and comes in a variety of different forms. The ones that we care about are gravitational potential, kinetic, and elastic potential. Within a closed system, energy is conserved and can be transferred between objects or transformed into different energy types. The conservation of energy allows us to calculate the different kinds of energies at different states within a system using basic energy formulas such as mgh, 1/2 mv squared, and 1/2 kd squared. Of course, those are for gravitational potential energy, the mgh, kinetic energy, 1/2 mv squared, and elastic potential, 1/2 kd squared. Alright guys, that's it for this video. Hopefully that was some good review of different energy types and the formulas that we use to calculate them, as well as how we can use conservation of energy to actually calculate different energies at different points within a system.